In this lesson, we will use calculus to compute the fluid pressure and fluid force on various objects. So for example, suppose you have a dam that has this type of shape. What we will learn in this lesson is how to compute the force of the water on that dam. So first, the definition of fluid pressure. The pressure P on an object at depth h in a liquid is P equals WH, where W is the weight density of the liquid per unit of volume. So, for example, for seawater, W is about equal to 64 pounds per cubic foot. And for regular H2O, W is about equal to 62.4 pounds per cubic foot. Now we're going to use something called Pascal's principle, and what Pascal's principle states is the following. If you have the fluid pressure exerted by a fluid at depth h is transmitted equally in all directions, so the pressure is equal in all directions. So the pressure exerted is equal in all directions, assuming you have the same depth. So the area of a piece of sheet metal is 5 square feet. The sheet is submerged horizontally in 10 feet of water. So what we have is sheet of metal, its area is 5 feet, and it's 10 feet down. Now the pressure is the force per unit of area, so force over area gives pressure, and that tells us that force is equal to pressure times the area. So to find the fluid force on the top side of this 5 square foot sheet of metal, we need to find first the pressure multiplied by the area. So we are in water, and they didn't say seawater, so we'll assume it's normal water. And that tells us that the weight density is 62.4 pounds per cubic foot. So my force is equal to pressure times area, and pressure is given by the weight density times the depth, so WH times A. So in this case, W is 62.4, the depth is 10, and the area is 5, and that gives me force is equal to 3,120. Let's figure out what its units are. So 62.4 has units pounds per cubic foot. 10 is the depth, that has units feet, and 5 is the area, that has units feet squared. So this tells us the force has a unit of pounds, which it should since it's a force. So next, let's assume we have some object that instead of being suspended in the water horizontally is suspended vertically. So something like this, some kind of shape. And we'll call this C, we'll call this D. Now I'm going to divide the interval from C to D into little pieces of width delta y. And I'm going to find the force on that piece. Now the force on that piece, we'll call it delta F sub I, is the weight density times the depth multiplied by the area. Now I'm going to make a function, we'll just call it h, and h of y as a function tells me the depth at y. So this particular depth is h of y sub I, so I have W h of y sub I. Now the area of this little box, I'll have another function that's defined as the length of the horizontal region, so this, that will be L of y sub I, that's the width of that box, multiplied by delta y. The total force is given by taking a limit of the sum from I equals 1 to n of all these individual pieces, so W, H of y sub I, L of y sub I, delta y. This gives us the W times the integral from C to D, H of y, L of y, dy. So what you will need to do to figure out the force exerted by the fluid on an object of this, some kind of shape like this, is find a function for the depth and a function for the length of your slice. The side of a tank has the shape of an isosceles trapezoid, 4 feet across the top and 2 feet across the bottom. So it looks like this, with a height of 3 feet. So 2, 3, and 4. Assume that the tank is full of water. What is the fluid force on the vertical side of the tank? So we are going to orient this such that this is my y-axis and that is my x-axis. That makes this the point 1, negative 3. This is the point 2, 0. Over here we have negative 2, 0. And over here we have negative 1, negative 3. And now we make a slice and compute the pressure on that slice. So first of all, the height function, or the depth function, we'll say, h of y will be negative y. So a depth of 1 corresponds to the y value of negative 1. A depth of 2 corresponds to a y value of negative 2. What I need to do now is to find a formula for the area, for the length of this piece. And you can do that using the fact that this is a line. So first find the slope of that line. M will equal negative 3 minus 0 over 1 minus 2. So m is equal to 3. The equation of the line will be given by y minus 0 equals 3x minus 2, or y equals 3x minus 6. If we solve that for x, we end up with x equals 1/3 y plus 2. Now 1/3 y plus 2 tells us the distance from here to here. So my length function, L of y, will be twice x, or 2/3 y plus 4. Now the force of the water on the side of this tank is given by the weight density of the liquid times the integral from C to D of the depth, h of y, times the length of a slice, L of y, dy. So here my weight density is 62.4 pounds per cubic foot. I have an integral from a y value of negative 3 to 0. H of y is negative y, multiplied by 2/3 y plus 4 dy. That gives us 62.4 integral negative 3 to 0, negative 2/3 y squared minus 4y dy. The details are worked out in the completed notes, but you should get 748.8. This is a force. Our units were, this weight density was given in pounds per cubic foot. This is in pounds. So next, suppose we want to find the fluid force on a vertical plate with the shape of a square with sides of length 4 meters that is submerged in 2 meters underwater. The weight density of water is 9,800 newtons. So here's what we have. We have a square with side lengths of 4 that is 2 meters underwater. Okay. Now, once again, we will have h of y So the depth at y equaling negative y. So a depth of, say, 3 is going to correspond to a y coordinate of negative 3. Now here, actually, L of y, the length of a slice, the slices always have the same length. L of y is equal to 4. Once again, the force is given by the weight density times the integral from c to d of h of y, L of y, dy. Now the weight density is 9,800, that should say newtons per cubic meter. So this is 9,800 times the integral from lowest y value -6, highest to -2, negative y times 4 dy. As I said earlier, the most important part is the setup, but we have 9,800 times -2y squared evaluated from -6 to -2, which gives you 627,200 newtons. In the next example, we suppose we have a circular observation window on a ship that has a radius of 2 feet, and the center of the window is 5 feet below the surface. What is the fluid force on the window? And we're going to assume that we're in the sea, so we have seawater, which has a weight density of 64 pounds per cubic foot. So first, let's draw a picture of what this window looks like. So I'm going to place the center of the circle at the origin. Now that gives us the equation x squared plus y squared equals 4. That's a circle of radius 2. So up 2, over 2, down 2, left 2. All right. And the water is 5 feet above it, so up at 5, that's where the water level is. Next, we need to find the function that gives us the depth, h of y. So when I plug in y equals 1, I need to be at a depth of 4. When I plug in y equals 2, I need to be at a depth of 3. So if this is my y, the depth is 5 minus y. Now next, I need a function for the length, and that's actually in this part not so bad. So L of y will equal, once again, 2x. And because you know that x squared plus y squared equals 4, we know that x is equal to the square root of 4 minus y squared. So the length function that I have, L of y, is 2 root 4 minus y squared. And thus my force is equal to W times the integral from c to d, h of y, L of y, dy, or 64 times the integral from -2 to 2, 5 minus y times the root of 4 minus y squared dy. And let's work this out. So let's compute the integral we derived in the last step. So first of all, I'm going to distribute the root 4 minus y squared and construct two integrals. So I will have 64 times the integral from -2 to 2 of 5 times the square root of 4 minus y squared dy, minus 64 times the integral from -2 to 2 of y times the root 4 minus y squared dy. Now this second integral, the function inside the integrand is an odd function, and you have a symmetric integral. So this will give us 0. If you do a u substitution for 4 minus y squared, you will end up getting the same thing. It's just a lot more work. Now this second one, first one we have 64 times 5. And remember that an integral is an area under a curve. This curve is a semicircle of radius 2. So we have that the area of that is 1/2 pi times 2 squared. So in the end we have 64 times 5 times 2 pi, which is 640 pi. In this case, our unit of force is pounds. A cylindrical gasoline tank is placed so that the axis of the cylinder is horizontal. So what that means is if I'm looking at the tank sort of head on, this is a circle and the tank extends back. Find the fluid force on the circular end of the tank if the tank is A, half full, and B, completely full, assuming the diameter is 4 feet and the gasoline weighs 42 pounds per square foot. So if the diameter is 4 feet, the radius is 2 feet. So this is 2, and an equation for that circle is x squared plus y squared equals 4. Next, we need an equation for the depth. Now, when we plug in y equals 2, we need to get a depth of 0. When we plug in y equals 1, we should have a depth of 1. When we plug in y equals 0, we should have a depth of 2. When we plug in y equals -1, our depth should be 3. So the depth is given by the function 2 minus y. So 2 minus the y value tells you the depth. So if you are corresponding to a y value -1, the depth is 2 minus -1, or 3. Now the length is very similar to the previous example. L of y is once again 2x, or twice the root 4 minus y squared. When we compute our force, we use the same equation, weight density times the integral from c to d of h of y times L of y dy. Now in this case, because my tank is half full, the bounds on my integral are -2 to 0. So y being -2 corresponds to the bottom, 0 is the halfway point, and the weight density is 42. So our integral is 42 times the integral from -2 to 0 of 2 minus y multiplied by 2 root 4 minus y squared dy. And this, when I distribute, just like we did in the previous example, I have 42 multiplied by the integral from -2 to 0, 4 root 4 minus y squared, minus the integral from -2 to 0 of 2y times the root 4 minus y squared dy. All right. Now, this first integral is now, instead of being a semicircle, it is a quarter circle, because my y's only go from -2 to 0. So the area of a quarter circle of radius 2, we will have 42 times 4 times 1/4 pi times 2 squared, or 42 times 4 pi, minus, now the second integral, -2 to 0, factor out that 2, y times the root 4 minus y squared dy. We have to use a u substitution to solve, so we will go through that together. You can no longer use the symmetry to conclude that this integral is 0 because of the fact that your interval is no longer symmetric. Let's finish computing this integral. Now to evaluate the second integral, we will let u equal 4 minus y squared. So du is -2y dy, or -1/2 du is equal to y dy. You also need to change your bounds. So if y is equal to -2, u is equal to 0. And if y is equal to 0, u is equal to 4. So we have 42 times the quantity, 4 pi, minus 2 times the integral from 0 to 4, -1/2 times u to the 1/2 du. The y dy gets replaced by -1/2 du. The 4 minus y squared is u. My bounds are replaced, and now I can antidifferentiate. So I have 42 times 4 pi plus the integral from 0 to 4 u to the 1/2 du. So that gives us 42 times 4 pi. The antiderivative of u to the 1/2 is u to the 3/2 times 2/3, evaluated from 0 to 4. And that gives us 42 times 4 pi plus 16/3, which when the 42 is distributed is 168 pi minus 200 plus 224 pounds, which is approximately equal to 751.788 pounds. Part B asks us to find the force if the entire tank is completely full. So what changes here are the bounds on my integral. So I still have the same functions though, 42. Now the integral goes from -2 to 2. 2 minus y times 2 square roots of 4 minus y squared dy. And this one's actually easier than the previous one. Factoring out that 2, I have 84 multiplied by the integral from -2 to 2 of 2 roots 4 minus y squared dy minus the integral from -2 to 2 of y root 4 minus y squared dy. Now this second integral, because of having the symmetric integral and an odd function, is 0. The first one is now a semicircle of radius 2, because the integral goes from -2 to 2 is the semicircle, not the quarter circle. So I have 84 multiplied by 2 multiplied by 1/2 pi r squared, so 1/2 pi times 2 squared. So that's 84 pi multiplied by 4, which gives us 336 pi pounds. And that's about equal to 1,055.575 pounds. And as you can see, the force on the bottom half and the top half are not equal because the depth makes the force on the bottom greater.